Welcome to the Deep Dive, the place where we cut through the noise, stack up the sources, and extract the truly crucial nuggets of knowledge custom tailored just for you. Today, we're plunging into the often hidden yet absolutely foundational world of data preprocessing and feature engineering. Every single day, you interact with data-driven insights, right? From personalized recommendations on your favorite streaming service to critical health diagnostics. But have you ever stopped to think about what happens before those insights are even possible? It's really about taking raw, often chaotic data and meticulously shaping it into something usable, something insightful. Our mission for this deep dive is, well, give you a shortcut, a way to understand the profound strategic choices involved in these crucial first steps in data science, turning confusing raw observations into clear, actionable information.
That's exactly right. And at its core, data is, simply observations of real-world phenomena. Imagine analyzing patient health records, right? Each lab result, every medication prescribed, maybe a patient's reported symptom, each one is a small window. But collectively, these observations, they paint a complex picture of health and disease. The fundamental challenge, though, is that raw data rarely arrives in the pristine, analytical-ready form we need. It's almost always, as we say, dirty.
Yeah.
And that dirtiness isn't just an annoyance. It fundamentally impacts the reliability of any analysis you might perform later on.
Okay, let's dive into that dirt. What makes data dirty in the first place, it sounds like?
Yeah.
Like we're saying, data is just born messy, not just occasionally.
In many real-world scenarios, it absolutely is, yeah. When we talk about data being dirty, we're generally looking at three pervasive issues, each with its own set of analytical headaches. First, data can be incomplete. This means you're missing attribute values, maybe an empty field for a patient's blood pressure reading, or even entire attributes you expected to capture. And if you're trying to predict patient outcomes and, say, half your records are missing critical lab results, well, your model's predictive power is severely hampered.
Right, makes sense.
Second, data can be noisy.
Noisy.
Yeah, this implies it contains errors or outliers. Picture a patient's age recorded as 250, or maybe a blood sugar level of -5.
Yeah.
These aren't just minor typos. They are values that can dramatically skew statistical measures, like means and standard deviations, basically leading your models to learn from garbage.
Uh-huh.
And finally, data can be inconsistent. This is where you find conflicting records, like a patient's birthday indicating they're 25, but their reported age is 45.
Ah.
Or maybe different departments use different codes for the same diagnosis. These inconsistencies create ambiguous signals, making it pretty much impossible for algorithms to derive clear patterns.
So this raises a crucial question then. Why does data get messy like this? Is it just people being sloppy? Or are there deeper, maybe more systemic reasons we need to consider?
That's a great question. It's rarely just sloppiness, though. Human error certainly contributes. Many common reasons for incomplete data, for instance, are systemic. Consider a survey where someone refuses to answer a sensitive question.
Right.
Or maybe a sensor malfunctioning intermittently during data collection. Perhaps a patient forgets a piece of their medical history, or a programming bug in a data entry system introduces errors. Sometimes seemingly obvious errors are deleted without proper notation, and that inadvertently creates missing values. The critical insight here is that data preprocessing isn't just a technical task, it's really a strategic curation step. It's about acknowledging this inherent messiness and making deliberate choices to transform the data into a state where it can genuinely inform accurate insights.
Okay, so once we accept that our data might be, well, a bit chaotic, what are our practical strategies for cleaning it up? Let's start with those missing values you highlighted earlier. What are the pitfalls and best practices there?
Right. Missing values are, just as they sound, simply empty cells in our data set where we expect information. But the real nuance comes in understanding why they're missing, because that why really dictates how you should handle them. We broadly categorize them into three types, and differentiating them is crucial for avoiding analytical traps.
Okay, three types.
First, missing completely at random, MEER. This is the ideal scenario, but often rare. It means the fact that a value is missing is purely random, no relationship to any other data observed or unobserved. Think of like a data entry clerk randomly skipping a field.
Gotcha.
Then there's missing at random, MAR. Here, the missingness is systematic, it can be explained by other observed variables in your data set. For example, maybe men are less likely to answer a particular health question, but you do have their gender recorded. The missingness depends on gender, which you've observed.
I see. So it's predictable based on other data we have.
Exactly. And finally, the most problematic one, Missing not at random, MNAR. Here, the missing values depend on unobserved data, or maybe even the value of the variable itself if it were observed. For instance, patients with very high blood pressure might simply refuse to report it. You don't see their high blood pressure value, and the missingness is directly related to that unobserved high value.
Wow, okay. That's a critical distinction. So once we've done our best to figure out the nature of the missingness, what are our actual options for dealing with it? Because it sounds like a one-size-fits-all solution could really harm the analysis.
You're absolutely right. One size definitely does not fit all, and this is where strategic decision-making is key. The simplest approach sometimes is if your analytical technique can handle them. Just keep them as they are. Some modern algorithms are designed for this.
Okay.
However, if your chosen method can't, you might consider removing data objects or rows with missing values. But, and this is a huge, but you have to be so careful, this can introduce severe bias. If your missing data is MR, or especially MNA, deleting those rows means you're systematically removing a particular subset of your population. That potentially distorts your entire data set, leading to, well, misleading conclusions.
So avoid removing rows for MAR, MNAR if possible.
Generally, yes, that's the strong recommendation. Another option is to remove attributes or columns with missing values. This is pretty drastic, usually reserved for when a single attribute has an overwhelming proportion of missing values, say, rough guess, maybe more than 25%, then imputation might just be meaningless noise.
Okay, so if a whole column is mostly empty, maybe just drop it.
Yeah, the signal-to-noise ratio might just be too low. But often the most nuanced and frequently the best approach for MR or MR types, especially when your tool needs complete data, is to estimate and impute a value.
Ah, filling in the blanks.
Exactly. Using sophisticated statistical methods to fill those empty cells. Simple methods, imputing with a mean, median, or mode. But more powerful techniques like regression analysis can predict missing values based on other features, or even using something like k-nearest neighbors to find similar data points and borrow their values.
Lots of options there.
Definitely. And the choice impacts the variance and distribution of your data, so it needs thought.
What's fascinating here, too, is that errors aren't just missing pieces. They're also values that just, don't fit. You mentioned outliers. How do we spot those anomalies, and what's the strategy for dealing with them, especially since some might be real, just rare?
Great point. Outliers are data objects whose values are simply too different, let's say, from the rest of the population. They can pop up from genuine errors like a faulty sensor recording an impossible temperature. Or they can be legitimate but rare events, like a patient with an unusually high but medically confirmed heart rate. The problem is, algorithms sensitive to range and distribution can be severely skewed by even a few extreme outliers. That leads to inaccurate models.
So how do we find them?
Often a mix of visual and statistical methods. For single variables, univariate techniques like box plots or histograms work well. For relationships between two variables, bivariate methods like scatter plots or contingency tables. And for more complex situations, multivariate approaches like cluster analysis can help find anomalies in higher dimensions.
And once we spot them, what then?
Well, the strategies mirror missing values a bit. You can do nothing if your analytical tools are robust to them. Tree-based models often are, for example.
Okay.
You can replace them with an upper or lower cap. It's a technique called Winsorization, useful when you want to keep the data point, but just sort of reduce its extreme influence, often used for univariate outliers.
So pull it back into range a bit.
Exactly. Or if you're absolutely certain it's an error and you have enough data that losing 1 point isn't critical, you can remove the data objects with outliers. The key really is to understand if an outlier is just noise you need to remove, or maybe a rare but important signal you need to manage carefully.
Okay, so we've meticulously cleaned our data. We filled in the blanks, dealt with the odd ones out. But sometimes even clean data can just be overwhelming, too big. Why do we need to reduce data? It feels a bit counterintuitive maybe to throw information away after all that work.
Yeah, I get why it feels that way, but it's not about careless disposal. It's about strategic optimization, especially now with big data. There are 3 core reasons for data reduction that directly impact model performance and, importantly, interpretability. First, for high-dimensional visualizations. Our human brains, well, we struggle to really grasp more than 3, maybe 5 dimensions at once on a chart. Reducing dimensions lets us actually see patterns.
Makes sense. Hard to plot 50 dimensions.
Exactly. Second, there's the very practical issue of computational cost. Datasets that are just excessively large can make algorithms grind to a halt or just take way too long to run.
Right, time and resources.
And third, This is a subtle but really profound challenge. The curse of dimensionality.
Okay, that sounds ominous.
It kind of is. It's not just about computation, it's about data sparsity.
Yeah.
In very high dimensional spaces, data points become incredibly sparse, almost lonely. Imagine trying to find two similar grains of sand on an infinitely vast beach. Every data point starts to look equally distant from every other point.
Ah.
This effectively blinds many statistical approaches and machine learning algorithms. They struggle to find meaningful patterns no matter how much data you technically have. So the objective of data reduction is twofold. Get a significantly smaller, more manageable data set while, and this is critical, closely maintaining the integrity of the original data. Avoid bias, avoid losing critical information.
That curse of dimensionality analogy really drives it home. The signal gets lost in the noise of too many dimensions.
Okay.
You mentioned two types, numerosity and dimensionality reduction. Let's talk about reducing rows versus numerosity. What are the smart ways to thin out the data set without losing its essence?
Right. For numerosity data reduction, focusing on reducing the number of data objects or rows, the technique choice often depends on your goals and data structure. Random sampling is the simplest. You just randomly pick a subset of data objects.
Quick and easy.
Yeah, great for cutting computational costs fast. But the risk is you might accidentally lose representation of smaller but maybe important subpopulations.
Oh, okay.
So to counter that, we often use stratified sampling. This also randomly selects data objects, but here's the key. It maintains the proportional representation of subpopulations in your sample. So if you're analyzing patient data and you know a certain rare disease group is crucial, stratified sampling makes sure their proportion stays the same in your smaller data set.
Much safer for preserving those important minorities.
Exactly. And then there's random over-under sampling. This is specifically designed to create a prescribed representation of subpopulations. It's incredibly useful for imbalanced data sets. Say you have very few examples of fraud compared to normal transactions. You might oversample the fraud cases or undersample the normal ones to give your model a more balanced signal to learn from.
Fascinating.
Okay.
So that's about making the data set smaller in terms of entries while keeping the right balance. Now let's shift to dimensionality reduction, reducing the number of attributes, the columns. You highlighted the curse of dimensionality. How do we effectively cut down features without losing vital info?
Right, this is where feature selection and feature extraction come in. Two fundamentally different philosophies, really, for tackling high dimensionality. Feature selection aims to find the most relevant subset of your original input variables. The art here is figuring out which existing columns truly help your model and which are just redundant or adding noise.
Okay, now here's where it gets really interesting, I think. Let's start with feature selection. What are the advanced strategies for picking those truly impactful variables? Seems crucial.
Absolutely. With feature selection, we typically talk about three broad strategies. First, the filter strategy. These methods are used as a pre-processing step, and they're completely independent of whatever machine learning algorithm you plan to use later. You select features based purely on statistical tests, things that measure their correlation with the outcome variable or their intrinsic information content.
So you filter them before you even choose your model.
Exactly. For example, the chi-square test X2. It's great for categorical variables. It tests the relationship between them by comparing observed frequencies to what you'd expect by chance. You pick the features with the strongest scores.
Okay.
For continuous variables, the correlation coefficient, like Pearson's, is invaluable. The key idea here, you want variables that are highly correlated with your target variable,
Makes sense.
but crucially, uncorrelated among themselves. If two predictor variables are tightly correlated, they're basically telling you the same thing. They're redundant.
Oh.
So you can often rank one without losing much predictive power, which simplifies your model and helps prevent overfitting.
Clever. Okay, that's the filter strategy. What's next?
The second is the wrapper strategy. Now, unlike filter methods, the selection process here is intrinsically tied to a specific machine learning algorithm. You're literally wrapping the feature selection around your chosen model.
How does that work?
Well, it involves searching through different subsets of features, and for each subset, you actually train and evaluate the performance of your specific classifier or regressor. Think of forward feature selection. You start with no features. Then you iteratively add the one feature that gives the biggest performance boost when combined with the features you've already selected. You stop when adding more features doesn't help.
So build it up piece by piece.
Right. And the opposite is backward feature elimination. Start with all the features. Build a model. Then iteratively remove the one feature whose absence results in the best model performance or the smallest drop.
tear it down piece by piece.
Exactly. This is often useful for models like linear or logistic regression where feature interactions matter. The big downside: wrapper methods can be computationally very expensive because you're training lots of models.
I can imagine. What's the third strategy?
The third is the embedded strategy. These methods are quite clever. They try to combine the benefits of both wrapper and filter approaches, keeping computational costs more reasonable. Feature selection happens as part of the model training process itself. It's iterative. Algorithms like lasso and ridge regression are prime examples.
I've heard of those.
Yeah, they have these inbuilt penalization functions. What they do is effectively shrink the coefficients of less important features towards zero, sometimes exactly to zero. So they perform feature selection automatically while they're training, and they help reduce overfitting at the same time.
Very efficient.
It is. And beyond these core strategies, techniques like random forests can also be powerful for dimensionality reduction.
How does a random forest do that?
Well, it builds many, many small decision trees. And it can inherently measure the importance of each feature based on how often and how effectively that feature is used to split the data across all those little trees. This gives you a really robust, model-based ranking of which features matter most.
Okay, so if we connect this back, feature selection is all about getting to the essence by carefully picking the best existing columns. But you also mentioned feature extraction. That sounds different. Like we're not just picking features, but actually creating new ones. How does that work? When would you do that?
Exactly right. Feature extraction takes a different conceptual path. Instead of just selecting a subset of your existing variables, it transforms your data from a high-dimensional space into a lower-dimensional one. It does this by finding a smaller set of new variables. And critically, each of these new variables is a combination of the original input variables. The goal is that these new, fewer variables collectively capture the same core information, the same underlying structure, as the original bigger set. It's about finding latent patterns.
Okay, creating new combined features. What's a common example?
The most common, almost a textbook example, is principal component analysis, or PCA.
PCA, right?
PCA is a linear dimensionality reduction technique. It transforms a set of, say, p-correlated original variables into a smaller number, k, of uncorrelated new variables. We call these principal components. How? It finds the directions in your data that capture the most variance, the most spread. The first principal component, PC1, explains the maximum possible variance. Then PC2 explains the maximum remaining variance, and it's constructed to be totally uncorrelated with PC1. And so on for PC3, PC4, down to K components.
So it reorients the data to capture the most information in fewer dimensions.
Precisely. PCA is incredibly powerful for reducing complex data sets, especially where many original features are correlated, multicollinearity. The trade-off, though, is interpretability. These new principal components are mathematical combinations. They might not have an obvious real-world meaning like your original age or blood pressure features.
That makes sense. A powerful tool, but you lose some direct meaning. Okay, finally, once data is meticulously cleaned, efficiently sized, sometimes we need to change its form entirely to make it optimal for certain algorithms. Let's talk about data transformation. What are the common tasks here, and why are they so critical?
Right. Data transformation is kind of the final polish. It ensures your data is in the precise format and scale required by specific analytical techniques. Some really common, often essential tasks include normalization and standardization.
Okay, heard those terms. What's the difference?
Good question. Normalization typically rescales values into a fixed range, very often between 0 and 1. Standardization, on the other hand, rescales data so it has a mean of 0 and a standard deviation of 1. It centers the data.
And when do we need these?
You use them when your analytical techniques are sensitive to the scale of features. Think about distance-based algorithms like k-nearest neighbors, support vector machines, or k-means clustering.
Distance calculations.
Exactly. If one feature ranges from 0 to 10,000 and another from 0 to 1, the first feature will totally dominate any distance calculation, right? Normalization or standardization puts them on an equal footing.
Got it.
Also, for techniques like PCA, which relies on variance, features with much higher variance would otherwise have a disproportionate influence on the principal components. Standardization fixes that.
Okay. What other transformations are common?
Other critical ones include things like binary coding, ranking transformation, and discretization. These are often used when you need to convert numerical data to categorical or vice versa, or maybe just simplify continuous data. Discretization, for instance, is about converting numerical attributes into bins or intervals, like turning exact age into age groups. For example, 20, 29, 30, 39.
How do you decide on the bins?
That's a strategic decision. You could use equal width, where each bin covers the same range, like 0, 10, 10, 20, 20, 30, good for uniform data. Or equal frequency, where you aim for roughly the same number of data points in each bin, better for skewed data. Or sometimes an ad hoc approach, where the cutoff points are based on specific domain knowledge. Maybe there are clinically relevant thresholds for blood pressure that define meaningful bins. The choice really impacts model performance and how easy it is to interpret.
So even making bins requires thought.
Oh, absolutely. And then there's attribute construction. This is where some real artistry can come in, I think. You use knowledge about the original attributes, or maybe combine multiple attributes, to create new, potentially more accurate or informative data features.
Like creating something new from existing pieces.
Exactly. Instead of just using a patient's raw height and weight, you might calculate their body mass index, BMI. BMI is often a single, more clinically meaningful attribute for assessing health than height and weight separately.
Right, combines them usefully.
Or if you have a date of birth and an admission date, you construct a new attribute, patient age at admission. That's often far more relevant for predicting a clinical outcome than the raw dates themselves. These transformations aren't just technical steps. They're often where deep domain expertise transforms raw numbers into powerful predictive signals.
Wow, what a journey we've just taken from grappling with the inherent, well, messiness of raw data.
Yeah.
Through all those crucial tactical decisions in cleaning it up, strategically reducing its size and dimensions, and then finally transforming it into the perfect shape for whatever analysis comes next.
It truly highlights the immense, often invisible work, doesn't it? It forms the bedrock of accurate, actionable insights. Think of it like, I don't know, the meticulous preparation an artist does with their canvas and paints before they even think about making the first stroke. Without these pre-processing and feature engineering steps, even the most sophisticated machine learning algorithms would be, essentially, trying to paint a masterpiece with blurry vision on a warped canvas. It just wouldn't work well.
Absolutely, that's a great analogy. So next time you encounter a striking statistic, or maybe a powerful data visualization, maybe pause and consider the hidden artistry, the painstaking strategic effort that went into preparing that raw data. What crucial insights might still be waiting, perhaps subtly obscured in the dirty data we haven't quite figured out how to handle yet? Or maybe what potential misunderstandings could arise if data isn't pre-processed with the right strategic care? It's truly foundational, isn't it? Influencing the conclusions drawn in practically every field, from precision medicine to financial markets, really makes you think.